Hello and welcome back to VHB tutorials. In previous video we had discussed about the heat conduction through hollow cylinder, and with that we had derived the formula for thermal resistance in case of hollow cylinder. And in that video I had promised that I will also solve the heat conduction formula for hollow cylinder by Fourier's law. So today I will do that, and along with that I will also solve the formulas of heat conduction through composite cylinders. So in case of composite cylinders we will see the cases of convection and conduction together, right? So I hope you will be with me till the end. Please don't skip any minutes of this video. Watch each and every minutes, right, to get the clear idea of this concept. And please follow me on the Instagram. Also subscribe to my channel if you are new, and please share this video as much as you can, right? And if you have doubts, then please ask me in the comment section. So without any further delay, let's get started. So first we will see the heat conduction formula by Fourier's law in case of hollow cylinder. The parameters are same, that is T1 is the temperature of the inner wall of the hollow cylinder, T2 is the temperature of the outer wall of the hollow cylinder, R1 and R2 are the inner and outer area respectively. We had considered the element of the hollow cylinder having thickness dr at a distance r from the center. And as we know that T1 is greater than T2, so heat will flow from inside to outside. This is the direction of heat flow, and we are considering only one directional heat flow, that is along the radial direction, right? So we will start. So first we will write that is by Fourier's law. First step we have to write that by Fourier's law. What is the Fourier's law? Q is equals to minus Ka dt by dx. Now here we are considering only one directional heat flow, and that is along the radial direction. So I will replace this x by r. So Q is equals to minus Ka into dt by dr. So K is the thermal conductivity of this hollow cylinder, and the material of this hollow cylinder is isotropic and homogeneous. So K is uniform throughout this hollow cylinder. Now I want to ask you one question, that what will be the temperature distribution in case of hollow cylinder? If you know the answer, then please write in the comment section, and if you don't know, then also ask me in the comment section, I will reply. Now first we will see what is the area. So this A is the area which is perpendicular to the heat flow. So perpendicular to the heat flow will be this area, okay? This is the area of the cylinder. Now what will be the area of the cylinder? It will be 2 pi. Now here we are considering the area of the element, not the whole hollow cylinder. We are first applying all our derivation on the elemental hollow cylinder. So what will be the radius of the elemental hollow cylinder? It is r. So 2 pi r into L. L is the length of this hollow cylinder. So L will be the length of the elemental cylinder also. So dt by dr. We are writing the formula for A only. Now we will put this formula in the above equation. So it will be minus K into 2 pi r into L into dt upon dr. Now we will separate, or we will arrange this formula in variable separable form. Variable separable form means taking the variables which are same on the other side and the other variables are on the different side, right? So here we have r, so we will take r on the other side. Now one thing I just forgot to say, that we are considering the steady state heat conduction. Now I will revise all the assumptions. That is, first is one directional heat flow. Our assumptions are one directional heat flow. Second, there is no internal heat generation. Third, steady state heat conduction we have. And fourth, our material is homogeneous and isotropic. So as we have steady state heat conduction, so Q will be constant, K will be constant. Why? Because we have homogeneous and isotropic material. Now we will bring this equation in the variable separable form. So Q into dr upon r. This dr goes on the left hand side and this r goes in the denominator of the left hand side. It is equals to minus K 2 pi L into dt. So we got the variable separable form. So you can observe that we have the one variable type on the one side and other variable type, that is d, on the other side. Now we will integrate. So you have to write here integrating the above equation. You have to write a statement that integrating the above equation, then after you have to perform this step. Q into dr upon r is equals to integration minus k 2 pi L into dt. Now when you use this Fourier's law, then we have to apply the integration boundaries. So for r we have r1 to r2. For t, why t? Because dt, t is only the variable on the right hand side. So we will put the variables, that is t1 to t2. Now again one question, that why I had written t1 and t2 on different levels. I will answer that because as t1 is greater than t2, so I had put a notation that t1 is above t2, so we can differentiate that t1 is higher than t2. Now I have to rub this part. So as q is constant, so I will bring out of the integration. So I will write here q into integration dr upon r is equals to this k 2 pi L is the constant term. So I will bring out of the integration. So it is minus k 2 pi L into dt t1 to t2. So q into, what will be the integration of 1 upon r? It will be log r. So ln r is equals to minus k 2 pi L into t from t1 to t2. So one thing I forgot, so I will write here r1 to r2, here also r1 to r2. So q into ln of r2 minus ln of r1 is equals to minus k 2 pi L into t2 minus t1. Now what will be log of a minus log b? It will be log a upon b. So it will be ln of r2 upon r1 is equals to, this minus side I will bring in the bracket, so it will be t1 minus t2. So k 2 pi L into t1 minus t2. So now we are getting our beautiful equation of q. So it will be q is equals to 2 pi k L into t1 minus t2 upon ln of r2 upon r1. So this is our equation, that is heat conduction in case of hollow cylinder. This same equation we are getting in the previous video when we had discussed this derivation by general heat conduction method. So now I hope you got the whole derivation clearly. So I know that you find this derivation very easy, so you will prefer this derivation to write in the university examination. Yes, it is also correct to write this derivation, but when you got the question in the university examination which have 7 marks, then you have to go for more steps. So that more steps are included in the general heat conduction method. So you have to go for that method to get the whole 7 marks. And if the question is asked for only 3 or 4 marks, then you can go for this method. This includes less steps and it will save your time also. So I hope you got the idea. Now using this same equation we can get the formula for RTH also. So Q is equals to T1 minus T2 upon 2 pi KL into ln of R2 by R1. Let's say this is equation 2 and Q is equals to delta T upon RTH. This equation is famous, and this is equation 3. Comparing equation 2 and equation 3, we are getting RTH as 1 upon 2 pi KL into ln of R2 by R1. So this is about the heat conduction in case of hollow cylinder. So now we will start our today's topic, that is heat conduction through composite cylinder. Now for that you have to consider a scenario, that consider this is the pipe of the boiler. In that pipe we have hot fluid. Now this hot fluid is used to heat the surrounding air. So this is the pipe, in that we have the hot fluid, and this hot fluid is used to heat the surrounding air. Now this hot fluid have 2 layers, that is first is layer A and second is layer B. Means we have 2 different layers having 2 different thermal conductivities, let's say Ka and Kb. Now in this hollow pipe we have the hot fluid, and which is used to to heat the surrounding air or surrounding fluid. So in this hollow pipe we have the hot fluid having temperature THF. THF is nothing but temperature of the hot fluid, and as this hot fluid and as this is the hot fluid, so it will have the thermal coefficient, that is heat transfer coefficient of hot fluid, that is HHF. HHF is the heat transfer coefficient of hot fluid. Now we will see that how the heat will transfer one by one. Now first consider this is the hot fluid having temperature THF. This T1, T2, T3 and TCF are the temperatures which are lower than THF, right? This T1, T2 and T3 are the temperatures of point 1, 2 and 3. This TCF is the temperature of surrounding air, or we can say TCF is the temperature of cold fluid or the temperature of atmosphere. Now as this temperature is higher, so heat will move in this direction. So this is the radial direction. In previous videos I had told that when you see the case of cylinder, then always consider the direction of heat flow is along the radial direction. So this is the direction of heat flow. So now the heat will flow from hot fluid to this innermost layer of the hollow cylinder. Now as the material or as the state of the hot fluid is what? It is fluid, and the innermost wall of the hollow cylinder is solid. So we have two different mediums. Whenever we have two different mediums and between that mediums we have heat transfer, then by what phenomena the heat transfer will occur between two different mediums? So it will be by convection. So first heat will transfer by convection to this innermost wall of the hollow cylinder. Now after reaching this innermost wall, the heat will move further. Now you can see here, we can see the heat transfer between the solid and solid medium, that is the innermost wall and the intermediate wall of the hollow cylinder. So when the heat transfer occurs between the two same mediums, then what type of heat transfer we can say? That heat transfer takes place by conduction. Now as this heat is reached at T2, or temperature means as the heat is reached at point 2, that is the intermediate wall of the hollow cylinder, and now it has to move further. So again we have the same mediums, that is the intermediate wall and the outermost wall of the hollow cylinder. So we have the same mediums, so we can see the heat transfer by conduction. So here also we can see the heat transfer by conduction from point 2 to point 3. Now the heat wants to go out. So again you can see we have this solid medium, and outside this solid medium we have the atmospheric air or cold fluid in general. So when the heat transfer takes place between two different mediums, then we can say that heat transfer takes place by what? Convection. So from point 3 to the cold fluid, we can see we have heat transfer by convection. So in here we have two different modes of heat transfer, that is by conduction and convection. So HHF is the heat transfer coefficient of hot fluid, HCF is the heat transfer coefficient of cold fluid, and K is the thermal conductivity of layer A, Kb is the thermal conductivity of layer B. You have to write this data when you start the derivation. So now we will write each of the equation of heat transfer separately. So first from hot fluid to the layer 1, we will write the heat transfer rate for the hot fluid to the layer 1. So we have what type of heat transfer? Convection. So convection is given by what? Q is equals to HA delta T. This is the formula of heat transfer by convection. So Q is equals to, what is the heat transfer coefficient of hot fluid? It is HHF, right? Into area. Okay, I will write the formula of area. So it is 2 pi, what is the radius? That is R1. So 2 pi R1 into L, that is the length of the hollow cylinder or this combination, into temperature difference. So it will be THF minus T1. So this is the equation first. Now we want to see the heat transfer between point 1 to point 2. So we have same mediums, that is solid walls. So again we will have heat conduction. So what is the formula of heat conduction? It is for cylinder. Now only I had derived that formula. So what was that formula? It is temperature difference. So T1 minus T2 upon 1 upon 2 pi Ka into L into ln of, what will be the ratio? It will be R2 by R1, right? So this is the equation 2. Now we want to see the heat transfer between point 2 to point 3. So as we have same mediums between point 2 and point 3, so we will again write the formula by conduction. So it is Q is equals to, what is the temperature difference? It is T2 minus T3 upon 1 upon 2 pi Kb into L. Okay, here Ka is the thermal conductivity of layer A and Kb is the thermal conductivity of layer B. So Kb, why Kb? Because we are sorry, because we are writing the heat transfer rate formula for point 2 and point 3. So the material which is between point 2 and point 3 have the thermal conductivity Kb. So Kb into L into ln of R3 upon R2. Now we want to see the heat transfer rate between point 3 and the atmospheric air. So here we have two different mediums. So whenever we have two different mediums, so we will use what formula? Which formula? So we will use this convection formula. So here Q is equals to HCF, that is heat transfer coefficient of cold fluid, into A. Area is 2 pi. Now what will be the radius? It will be R3. 2 pi R3 into L into temperature difference will be T3 minus TCF. So this is equation number 3 and 4. Now you will wonder that why I had written Q, Q, Q in all the equations. Is the rate same for this both the walls, means both the layers? Yes. Why? Because these layers are in series combination. So whenever the layers are in series combination, then throughout that layer we can see the heat transfer rate is constant. So remember that in majority cases of cylindrical pipes, you will find this series combination only. So the heat transfer rate throughout the combination will remain constant, right? Now the next step will be bringing this temperature difference terms on the other side and the other terms on the different side. So from equation 1, I will bring this temperature term on the other side. So it is THF minus T1. You have to write from equation 1. Then you write this step. So THF minus T1 is equals to Q divided by this whole term, HHF into 2 pi R1 into L. Let's say this is equation number 5. Now from equation 2, again you have to write a line that from equation 2, then you perform this step, that is T1 minus T2 is equals to Q into 1 upon 2 pi KL KAL into ln of R2 upon R1. Let's say this is equation number 6. Now again from equation 3, we will write T2 minus T3 is equals to Q into 1 upon 2 pi Kb into L into ln of R3 upon R2, equation number 7. Now the last equation is remaining. So from equation 4, we will write T3 minus TCF is equals to Q divided by HCF into 2 pi R3 into L. So this is equation number 8. So from equation 5, 6, 7, 8, we can think that now we have to do which step. So we will add all these equations. So for that I have to rub this part. So when you add equation 5, 6, 7 and 8, you will get THF minus TCF. These two terms will remain all the other terms will be cancelled. So you have to write one line that adding equation 5, 6, 7 and 8, THF minus TCF is equals to okay, this Q upon L and 2 pi is the common in all these 4 equations. So I will bring out. So Q upon 2 pi L out of the equation. So it will be what? It is 1 upon HHF into R1 plus the second equation will be 1 upon Ka, or we can write Ka into ln of rho. Ln is in the numerator. So ln of R2 upon R1 upon Ka plus the seventh equation will be ln of R3 upon R2 divided by Kb, and the last is this. So plus 1 upon HCF into R3, right? So this is the whole equation. So I will rub this part. Now I will write properly first. So it is 1 upon HHF into R1 into ln of R2 by R1 into Ka plus ln of R3 by R2 upon Kb plus 1 upon HCF into R3. Right? We have this equation. Now from this equation we want the formula of Q. So we will bring Q on the other side. So Q is equals to 2 pi L into THF minus TCF is upon 1 upon HHF into R1 plus ln of R2 by R1 upon Ka plus ln of R3 upon R2 upon Kb plus 1 upon HCF into R3. So this is the formula of Q, that is heat conduction in case of composite cylinders. Now I will write a general form that if there are n cylinders, n composite cylinders, then the formula of Q can be written as Q is equals to 2 pi L into THF minus TCF upon 1 upon HHF into R1 plus 1 upon sigma n takes value 1 to n into ln of 1 upon K n into ln of R n plus 1 upon Rn plus 1 upon HCF into Rn plus 1. So this will be the formula when we have n composite cylinders. Now suppose that if we don't have the inside and outside heat transfer coefficient, that is HHF is not there and HCF is not there. So how we will write this formula? So observe it. So you have to write that if the inside and outside heat transfer coefficients are not given, I will write if are not given, then Q is equals to 2 pi L into T1 minus L into T1 minus Tn plus 1 upon 1 upon, or let's say sigma n takes value 1 to n into 1 upon K n into ln of R n plus 1 upon Rn will be this equation, right? So we had removed the part of HHF and HCF because it is not given in the equation. So if inside and outside heat transfer coefficient are not given, then only we have to write this formula that Q is equals to 2 pi L into T1 minus Tn plus 1. That what is T1? T1 is the innermost temperature of the hollow cylinder, and this Tn plus 1 means the outermost temperature of the hollow cylinder. So we have to consider the innermost temperature and the outermost temperature. The intermediate temperatures are not considered. So T1 minus Tn plus 1 upon sigma n takes value 1 to n, 1 upon Kn into ln of Rn plus 1 upon Rn. So we will use this formula when the inside and outside heat transfer coefficients are not given. Now the last part, but not the least, that this is the important part, and this is applicable in the case of walls and in case of cylinders and in case of spherical walls also, right? So if there is steady state heat conduction, one dimensional heat flow and no internal heat generation, then only we can draw the thermal circuit and we can use the thermal resistance concept. That means when we have a system which follows these assumptions, that is steady state heat conduction is there will be no internal heat generation, and the last is there is one dimensional heat flow. When these three conditions are satisfied by any of the systems of the heat transfer concept, then we can use this thermal circuit. We can draw the thermal circuit for that system when we have these three conditions satisfied. And if these three conditions are not satisfied, then we cannot draw the thermal circuit and we cannot find the formula, or we cannot find the value of thermal resistance. So this is the important point. Note it down. So that's all for today. So that's all. I hope you had enjoyed this lecture. If you have any doubts, then please ask me in the comment section. Also follow me on the Instagram. I had provided the link in the description. And in next video, we will see the critical radius and critical thickness. So have a good day and bye until next video.